the current from the lamp will now be 0. And then which of these equations is the best to use then for the lamp?
I guess any of them with the I in there would be fine.
Well, can we assume that the resistance of the lamp is constant?
Yeah.
Yeah, so this would be a good equation to use. But can we assume that the voltage across the lamp is constant? Would these two lamps have the same voltage? And the first thing to say is, if it's not obvious, then this is not a good equation to use, right? Since we have one equation we know is working, we shouldn't use this, but there's no reason to think now that these voltages are going to be the same. For one thing, right now there's a voltage drop here. But because these are in parallel, they have to have the same voltage drop. So now the voltage drop across here must be 0. In fact, you can see that from Ohm's law. Now that the current across the lamp is 0, its voltage drop has to be 0.
So all the drop comes from the other resistor?
That's right. In any case, this is not the best equation to use here now, because it has two things that are changing. We want to pick out an equation where definitely only one thing is changing. So I squared times R is a much better equation to use for the lamp. Now what would this say is the power across the lamp? Right. That was pretty obvious anyway. Obviously if something has no current, it has no power. But now we can work that out mathematically. You could use these other equations, but they're a little bit more subtle. So it's better to use this equation where there's only one variable changing. No power across the lamp. This is the idea of a short circuit. We don't want this short circuit because it bypasses the lamp. So the power across the lamp here would fall to 0. Now, what would happen here to the power delivered by the battery? That would also be a good question. If we put in the short circuit here, what's happening to the power delivered by the battery? Let's try working that out on paper.
So now if you open that other path, the resistors aren't in parallel anymore? I mean series anymore, or are they still in series?
These two here?
Now they're not.
That's true. That's right. These were in series. Remember that series means there's a twofold test. Any current from here must go through here, and any current coming into here must have come from here. Well, that was the case here because this path was closed. But now, current that comes out of this resistor does not have to go through the second resistor. So you're right, they're no longer in series. Whether things are in series or not definitely depends on the other possible paths.
So you can't, but now you can kind of think about it like that lamp, that one isn't even there.
That's true.
So
that's a good analysis.
So the resistance that the battery,
What's happened to the equivalent resistance that the battery sees?
is it changed? Well, it's as if before you had, let's say from before they were in series, so you added them,
Right?
but now you only have one, so it's like there's less.
Yeah, that's right. So here, the total resistance was this resistance plus this resistance. But what's the total resistance in this circuit?
Just the one.
Yeah, it's just the resistance from this one resistor. There's no current going through the lamp. So it's just this resistance plus the 0 resistance from here. So the equivalent resistance has gone down. Like you said, it's as if the lamp wasn't even here anymore. Or just in more common sense terms, we've now opened up a really easy path for the electricity to flow through. So clearly there's less resistance. We've opened up a really easy path for the current to flow through, so clearly there must be less resistance than before. That was a good start. Now that we know that the equivalent resistance perceived by the battery has gone down, how can we figure out what's happened to the power delivered by the battery?
It's going to go up.
Which equation are you using?
Which is square R.
Now, why is that the right equation to use?
Because you know that the V is constant.
That's right. This is a much better equation to use than this one, because we haven't figured out what's happened to the current from the battery. That might mess us up. This is not the best equation either. This is the key equation to use here. Now we know that this denominator has gone down. So what did you say has happened to the power from the battery? That's right. Well, this shows you how important it is to focus on which device the question is asking about. What's happened to the power being delivered to this lamp? It's fallen to zero. But what's happened to the power that the battery is delivering? It's increased.
Yeah.
So the power can totally change. Again, that should make sense. Why is there no more power going to this lamp? Because there's a perfectly easy alternative path for the electricity to go through. But why is the battery delivering more power? Because with this easy path, there's less resistance. So it's easier for it. The smaller the resistance, the more current the battery wants to deliver. The smaller the resistance, the more current the battery wants to deliver. So another good question, this could be a lamp too. Well, what's happened to the brightness of this top lamp when we close the switch?
Well, then the resistance of that lamp didn't change.
That's right.
And now if we're trying to think of the current through it then. So the voltage through that lamp went up because now all the drop is through that one.
Right.
And the resistance of it didn't change. So the current through it had to go up too, so the power, so it's brighter.
That's right. After all, if the battery is delivering more power, but it's not delivering power to this lamp, it must be really delivering a lot more power to the top lamp. I guess we could call this lamp A, and this is lamp B. So before we were working with lamp B. So which of these equations is the best one to use for lamp B? It's not so obvious to me. Well, actually, the easiest thing for me to think about here is all the power from the battery is going through this lamp.
Yeah.
So all the power from the battery is being dissipated through this lamp. So whatever happened to the battery is precisely the same as what's happening to lamp A. That's the easiest way to think about it. But you could also use one of these equations here. I guess this is a good equation to use. Either of these two equations. We could work out that both the voltage and the current have increased here, and the resistance hasn't changed, so the power has to have increased. As a reminder, the big lesson we've gotten here is when we're applying our equations, we have to be totally explicit about to which device we're applying the equation. And when we pick our equation for power, you have to keep in mind that more than one variable can be changing. So you have to pick the expression for power where hopefully only one thing is changing. These videos are offered on a pay-what-you-like basis. You can pay for the use of the videos at my website. There's a link to my website in the info box. The address is www.freelance-teacher.com/videos.htm, or you can just use the link in the info box. Thank you.